Hey, it's Nick here. So I want to do a short video on K-maps, Karnaugh maps, which are a way to simplify Boolean equations starting from a truth table, trying to come to typically a sum of products expression. So we started to talk about this in 250, but we ran out of time, so I said I would post a video going over all of the details that we didn't get to. So let's talk about K-maps. The basic thing we're after here is taking Boolean equations and simplifying them using this technique called a Karnaugh map or a K-map. And the usual setup is we have a truth table. So we have some function, say x of, and I'm going to pick on 4 variables here because it's the hardest case. If you only have 3 variables, it's easier to do, but it's exactly the same procedure. So we have a function x of 4 variables. And let's say this is the truth table for it. So suppose our truth table values are something like this. Okay, now we know we can write a sum of products expression by just writing a minterm everywhere that we want our output function to be a 1. So we could actually say that this is equal to, for example, this 1 here corresponds to the complement of A, ANDed with the complement of B, ANDed with C, ANDed with the complement of D. And we could add the minterm corresponding to this one down here, which is A bar, B, C, D bar, and so on. And we can write this in compact form as simply the sum of minterms 2, 6, 7, 10, 11, 12, and 15. And you have to actually, count these up and figure out which row corresponds to which minterm. But if I didn't make a mistake, those are the rows where we have 1s. Okay, so we can write this out. We can write a 4-element product for each of these minterms and put them all together in an OR gate. It's a lot of hardware, right? Each of these requires a 4-input AND gate, and we have 1, 2, 3, 4, 5, 6, 7. So we need 7 of those 4-input AND gates, and then we need a 7-input OR to take the sum of all of those. That's a lot of hardware. So we'd like to try to simplify this. And we can do it algebraically, we can do it by trial and error, we can also do it using a K-map. All right, step 1, begin with a truth table. Okay, we have our input values, all the possible combinations, and we know what the output value is from our truth table. That's the beginning point, okay? If you don't have a truth table but you have a description of a circuit, you have to write a truth table. All right, step 2, draw an empty K-map. That's what we have up here. For 4 input variables, this is always what your K-map's going to look like. It's going to be a 4x4 grid. And I can label these, A, B, C, D. I could label it A, B, C, D, or B, A. It's totally up to you. But you'll do it the same way every time, and that will make you very fast in making K-maps eventually. And the way we think of this, right, is this entry means A equals 0, B equals 0. This row means A equals 0, B equals 1. And we can think of, a little CD above each of these entries. So this column, for example, corresponds to C equals 1, D equals 0. This is C equals 1, D equals 1. Okay, and we'll see what we do with that in a few minutes. Now, when you draw this out, it's very important the order in which you write these column headings. It's got to be 0, 0, 0, 1, 1, 1, 1, 0, as opposed to the usual 0, 0, 0, 1, 1, 0, 1, 1. We put them in this order. This is something called a gray code. We'll talk about it later. But they've got to be in this precise order. Okay, third step, copy the 1s to the K-map. All right, how do we do that? It's a very mechanical procedure. The idea is, look at each one in your truth table. For each one we find here, we're going to place a 1 somewhere inside this K-map. And where we place it depends on the values of A, B, C, and D. So for example, this one right here, we want to place it where A and B are both 0, which means it's going to be somewhere in this top set of 4 boxes. And we want to place it where C and D are 1, 0, respectively. Well, CD 1, 0, that's this column right here. So this box right here corresponds to this entry of the truth table. Okay, 0, 0, 1, 0, 0, 0, 1, 0. So we transfer the 1 into this entry in the K-map. And we do that for each entry where we have a 1 in the output. So here is a 1. This corresponds to 0, 1, 1, 0. AB should be 0, 1. CD, again 1, 0. That's a 1 right here. 0, 1, 1, 1 will correspond to 0, 1, 1, 1. So that's this one right here. 1, 0, 1, 0, while AB is 1, 0, CD is 1, 0. That's right there. This last row above this line, 1, 0, 1, 1, AB is 1, 0, CD is 1, 1. There's a 1 right there. And we got two more, 1, 1, 0, 0, so 1, 1, 0, 0. And 1, 1, 1, 1, that's right here. Okay, now we filled in all the ones. We only fill in the ones, don't fill in the zeros. Alright, so copy the ones to the K-map, do not copy the zeros. Alright, the fourth step is what we call covering the ones. So we want to cover the ones in this K-map that we've made. And what does that mean? We're going to draw rectangles to enclose all of the ones that we've drawn in the K-map. But we have to follow a special set of rules. The first rule is we have to cover all of the ones. We can't leave any of them uncovered. The second rule is we're not allowed to cover any zeros. So any box that we haven't filled in is implicitly a 0. We're not allowed to cover any of those. However, we are allowed to cover a 1 more than once. We can have more than one rectangle that contains a 1. That's perfectly legitimate. The rectangles we draw have to have sides of length 1, 2, or 4. Okay, that's the width and the height. We can have a 1 by 2, we can have a 1 by 1, a 2 by 4, a 2 by 1. Those are all fine, but we cannot have, say, a 2 by 3. We also want to try to use the largest rectangles that we can. So if you could cover it with a set of small rectangles, but you can also cover it with larger rectangles, use the larger ones. But don't make them so large that we end up covering zeros. Okay, so the largest rectangles that you can legally use are the best ones to use. Along the same lines, try to use as few rectangles as you can. Okay, so you need to make sure you cover all the ones, but don't use any extra rectangles if you don't need to. So use large rectangles and use as few of them as possible. And now we're simply going to draw rectangles and try to enclose all of the ones. Well, there's one easy way to do this right away. I could simply draw a 1 by 1 rectangle here, a 1 by 1 here, a 1 by 1 here, and I could draw a total of 7 1 by 1 rectangles, and I would have covered all the ones. I wouldn't have covered any of the zeros. But why is that not a good solution? Because those 1 by 1 rectangles, I'm not using the largest rectangles I can. There are other ways to cover these using bigger rectangles. Okay, so this becomes a bit of a puzzle game, right? Start with the outliers. This rectangle right here, I can cover it with a 1 by 1. There's no 1 by 2 or 2 by 1 I can use to cover this. Okay, this is just going to have to be a solo cover. So we can get rid of that one. Take a look at this one in the corner though, right? I could cover it with a 1 by 1, but if I used a 1 by 2, I could cover that corner one and also cover another one next to it. Bigger rectangle is better. And now I don't need to cover this. I can if it helps, but I don't need to. Okay, same thing up here. I can cover this one and this one together with a single rectangle. And then in fact I can cover these two with a single rectangle. And now I have a perfectly good covering. Okay, it satisfies all the requirements. Each rectangle has a length, it's 1, 2, or 4. I've covered all the ones. I haven't covered any zeros, and I've used as few rectangles as possible. Now, you know, I could also draw a rectangle here to cover these two, and that's okay. I can cover these ones more than once, but I don't need to do that. I only need to cover each rectangle once. And that would be a solution, but it would be a solution with more rectangles. Fewer rectangles is preferable. So this is a really good covering, and it's not the only covering we could come up with probably, but it's a really good covering. Alright, now that we have our covering, what do we want to do? We want to write an equation for each of these boxes. So this is our next step. Alright, so our next step is to write a product term corresponding to each rectangle. And here's how we do that. Let's look at one of our rectangles, like this lower right rectangle right here. And let's observe the values of A, B, C, and D as we look at each point in this rectangle. So this rectangle, let's just look at A. So this box right here, A is equal to 1. This box here, A is equal to 1. So at every point in this rectangle, A is equal to 1. On the other hand, if we look at B, at this point, B is 0. And at this box, B is 0. So at both points in the rectangle, B is a 0. If we look at C, well, this rectangle corresponds to C equals 1. This rectangle corresponds to a column where C equals 1, so C is 1. If we look at D, this column corresponds to D equals 1. This column corresponds to D equals 0, so D is 0 or 1. Alright, so we identify the values of A, B, C, and D as we move around the inside of this rectangle. And we see that A is always 1, B is 0, C is 1. D can be either 0 or 1. Okay, any variable that can be either 0 or 1, we ignore. And now we write a minterm, something that looks like a minterm corresponding to these three values. So since A is 1, we write A. Since B is 0, we write B bar. Since C is 1, we write C. This product term corresponds to that rectangle. Alright, and we keep doing this. Let's look at this rectangle up here in the upper right corner. So A can be 0 or 0. So A equals 0. B can be 0 or 1. C is going to be 1 or 1, so C is 1. And D is 0 here and 0 here. D equals 0. So B we're going to ignore because it could be 0 or 1. A is 0, C is 1, D is 0. So this box up here corresponds to the expression A bar, C, D bar. And you just do this for each of your rectangles. So this rectangle over here, and I'll go a little faster here, A could be 0 or 1, so we don't care about A. B is a 1 here and a 1 here, so we're going to have a B. C is a 1 in both places, so we're going to have a C. And D is a 1 in both of these spots, so we're going to have a D. So that's the product term corresponding to this. And what about this last rectangle over here all by itself? Well, if we look at this, there's only one square in this rectangle. So A is equal to 1, so we'll write A. B is also equal to 1, so we'll write B. C is equal to 0, so we'll write C bar. And D is equal to 0, D bar. So that's the product term corresponding to this one. Well, if you think back to talking about minterms, this is the minterm corresponding to one of the rows in our truth table. Actually correspond to the row where A and B are 1 and C and D are 0. That's this row right here. So what we've written here is just the minterm for this one. That doesn't buy us anything, right? That's just minterm 12. But for these two ones, we wrote something simpler. Instead of writing the minterm for this and this, we combined them into a simpler expression. Alright, and then the last step is to sum those terms, or to OR them together, to get your final equation. So we're trying to write an equation for x, right? That's the expression in our truth table. It's just equal to the sum of these product terms corresponding to each rectangle. So x is equal to A, B bar, C, ORed with A bar, C, D bar, ORed with B, C, D, ORed with A, B, C bar, D bar. And that's your final answer. And that's all there is to it. Okay? It's a lot of steps. It's, you know, these 6 steps, and the covering of the ones takes some trial and error, but it's a very mechanical algorithm. Okay? You go through these steps, and at the end you get this equation, and this is a simplified equation. Remember, our direct sum of products would have been 7 things ORed together, where each of those things was an AND of 4 terms. Well, here we've got 4 things ORed together, 3 input, 3 input, 3 input, 4 input. Quite a bit less hardware. Okay, so this is a simpler circuit to build, which is good if you've got to build this on Tinkercad or actually put wires into a proto board. This is going to be faster, easier, less error prone. So that's the basic idea of a K-map. Alright, so next I want to look at a variation on covering these ones, which is what we call wrapping the edges or playing asteroids. Alright, so let's look at this truth table. Okay, this is a different function x, and I've already filled in the K-map values for you. So we have 6 K-map values corresponding to these 6 ones in our truth table. And if we were to try to cover these using the rules we've had so far, we could put a 2x1 rectangle here, a 2x1 here, and then a 1x1 and a 1x1. Okay, here's the cool thing about covering K-maps. It's like playing asteroids. This bottom edge is connected to this top edge, which means that we can actually draw a split rectangle which looks like this. Okay, so instead of having a 1x1 and a 1x1, we have a 2x1 now. And this makes sense because we could think of this rectangle, this 4x4 K-map, as being replicated down here. And if we did that, this one up here would be sitting in a little square right down here, and it would be pretty obvious, oh, there's a 2x1 rectangle that covers those. So if you think of this K-map as being replicated 4 times, that's all we're doing when we wrap. We're recognizing the fact that you know, there would be a 1 here, and we could draw a rectangle around that. So we can wrap the edges. So that's the last addition to our rules for making K-maps. So there's the extra part about covering the ones. You can wrap the edges, okay? Which means we can connect the top to the bottom, we can connect the left to the right. In this case, that works really well for us because we could do a 2x1 to cover this, we could do a 2x1 to cover this, but we could think of this edge being connected to here. We can do a 2x2 by wrapping like that. That's a bigger rectangle, 2x2 versus 2x1, and it's fewer rectangles, 1 big rectangle versus 2 little ones. That's a win on both of those rules. Alright, so what are the expressions corresponding to these rectangles? Well, this rectangle here, right, this is a 2 high, 1 wide. Let's look at the values of A, B, C, and D. So this box, A is 0, this box, A is 1. A can be 0 or 1, we ignore it. This box, B, is 0, this box, B, is 0. So B has to be 0, so we write B bar. And in both of these boxes, C is 1, so we write C. And both of these boxes, D is 1, so we write D. So there's a product term corresponding to this broken rectangle. Alright, the fun part is this rectangle here. So if we look at these 4 spots inside the rectangle and look at the values of our variables, well, here A is a 0, here A is a 1, we can stop right there. A can be 0 or 1, we're going to ignore A. Okay, here B is a 1, here B is a 1, here B is 1, and here B is 1. B is 1 everywhere, so we write a B. Let's look at C. Here C is a 0, here C is a 0, but here C is a 1. So C can be 0 or 1, we're going to ignore C. And our last variable D, well, in this box D is a 0, this box D is a 0, and this D is a 0, and D is a 0. D is 0 everywhere, so we write D bar. And now we can sum those together to write our expression for x, and x is just equal to B bar CD ORed with BD bar. And there you go, there's an expression for x. And significantly simpler than the straight sum of products, which would have had 1, 2, 3, 4, 6 input OR gate being fed by 6 4 input AND gates. Okay, and here we've got a 3 input AND, a 2 input AND, and a 2 input OR. So this is a lot simpler. And wrapping around the edges helps us do that simplification. So that's useful. All right, one more example of wrapping. So here's a truth table that corresponds to this K-map. And we know that, we can cover these with singleton squares. We can wrap like this, or we could wrap like that. But it turns out we can actually think of this as one 2x2 rectangle that's kind of exploded around the corners. And again, picture this K-map replicated over here. Okay, this one would be sitting right here. And if we replicated this K-map down here, this one would be sitting right here. And then if we put another copy of this K-map over here, this one would be sitting right here. And now it's really clear, oh, all four of those are adjacent to each other. So we can cover this original map with an exploded rectangle that looks like this, and that we think of as a 2x2 rectangle. So what equation do we get if we try to cover this rectangle? Well, look at the values of a, b, and c, and d at each point in the rectangle. So look at variable a. Here a is a 0, here a is a 1. We can stop there. A can be 0 or 1. We ignore a. Here b is a 0. In this box b is a 0. In this box b is a 0. This box b is a 0. B is always 0. So we'll write b bar. Here C is a 0, C is a 0, but here C is a 1, C is a 1, so C can be 0 or 1, ignore C. And D is a 0 here, and it's a 0 here and here, so D is always 0, so D bar. That's the only rectangle we need to cover all of our 1s, so we can write our equation for x. It's just B bar ANDed with D bar. And remember, this is not the same thing as BD, ANDed and then barred, okay? There's, two things being complemented and then ANDed together. So, B bar, big space in between, D bar. All right, here's a really nice truth table. Suppose we have a 1 in every single box here. So this corresponds to a case where we have 1s in every row of this truth table. Well, how would you cover this K-map? How would you cover the 1s? You would do it with just a single rectangle. It's a 4x4 rectangle. It's the best you can possibly do. And if you try to write a product term corresponding to this, well, A could be 0 or 1, B could be 0 or 1, C could be 0 or 1, and D could be 0 or 1. So none of the terms A, B, C, or D matter. So what is x equal to? It's just equal to a constant, and in this case it's equal to the constant 1. And the same thing happens if you have a truth table where you have zeros everywhere. There's no 1s to put in your K-map, so you can't draw any rectangles, so we have no product term. So what's the equation? It's just x equals a constant, and what constant is it? In this case it's the constant 0. So those are two sort of extreme endpoints in coverings of a K-map. Okay, here's your worst nightmare. This is a very pathological K-map, okay? If we try to cover our 1s with rectangles, no matter how clever we are, the only possibility is to draw a 1x1 around each of these. There's no way we can combine these and cover any of them with even a 2x1 or a 1x2. And if we have a 1x1 and we write the product term corresponding to, say, this one, we see that A is 1, B is 0, C is 0, D is 1. It's just a minterm again. So using a K-map to write an equation for x is just going to get us the plain unsimplified sum of products. Okay. Fortunately, when you have this checkerboard pattern, there's usually something else at play related to XORs. Could be an exclusive OR of 2 or more inputs, could be an exclusive NOR. But that's something to talk about another day, right? But these checkerboards, they don't cover well using K-maps and sum of products, but sometimes you can use an exclusive OR to do a succinct covering of them. All right, here's one more embellishment on this whole procedure, which is sometimes you have truth tables with what we call don't care values. There's various reasons you would have this in a truth table, but for example, it may be that we never expect this particular input combination to appear. And so in that case, we don't really care if our function generates a 0 or a 1. we can take advantage of that in K-maps. So we're going to add one more rule to our covering guidelines. So here's our one more rule. The don't cares can be covered, but you don't need to cover them. So cover them if it helps you with these other guidelines. If it helps you use larger rectangles or fewer rectangles, go ahead and cover these dashes. If it doesn't help you, just ignore them, because we don't care if they end up being zeros or ones. So how would we cover this K-map? Now, if we didn't have the don't cares, we would do a 1 by 2 and we'd do a 1 by 1. And that's a slightly simplified but still pretty complex expression. But the dashes, right, we can cover those with a 2 by 2. And here we can pick up this one and cover it with another dash. And there's a 2 by 1. And now we get a much simpler expression. Now, if you've been seeing a pattern when we write the product terms corresponding to these boxes, the more things we have covered, the smaller the expression. A 1 by 1 has 4 things ANDed together. A 1 by 2 or 2 by 1 has only 3 things. This has only 2 things. And if we have a 1 by 4, that's going to have 2 things. If we had a 2 by 4, that would only have 1 term in its product. So the bigger rectangles are better. And if it turned out that we had, say, a dash over here, we would simply ignore it. We could cover it with a 1 by 1, but we don't need to, and that would give us an extra rectangle. So fewer rectangles is better. All right, that's pretty much the whole procedure for using a K-map to find a simplified sum of products representation of a function. So follow those steps, work methodically, work carefully, and you can get simpler equations out the other side, and that's useful before you're actually building a circuit. Start with something simpler. Another possibility is we want to use a K-map to find a simplified product of sums. And if you have a truth table which has mostly ones in it, a sum of products is going to be generally pretty complex because, unsimplified, we have a minterm for each of these ones. A product of sums. So another possibility with a K-map is to use a K-map to make a simplified product of sums expression. So remember, we can do a sum of products and write a minterm everywhere that we have a 1 in our output variable. But if you have a lot of ones, that's a lot of minterms. And you can simplify it with a K-map, but it may be simpler to do a product of sums where we're only interested in the 0 terms. So using a K-map for a product of sums is the exact same collection of steps, but it's a dual process. Sums get replaced with products, products get replaced with sums, complements switch around, zeros and ones switch around. And so it looks something like this. If we want to do a simplified product of sums, we copy the zeros into the K-map. So we have 3 zeros here. So 0, 0, 1, 1, that's a 0 right here. 0, 1, 1, 1, that's a 0 right here. And 1, 1, 1, 1, that's a 0 right here. So we copy the zeros, we do not copy the ones. If we have don't cares, we're still going to copy those. And now we try to cover the ones using our same rules. And there's not a lot of choice about how to cover these. I can put a 2 by 1 rectangle here. And I can cover this with a 1 by 1, but I can use a 2 by 1 because I'm allowed to cover things more than once. So bigger rectangles are better. Right, so now I've got 2 largest rectangles I can use to cover all the zeros. I've only covered the zeros, I have not covered the ones. Multiple covers are okay. So there's a really good optimal covering of the zeros. And now we write a sum term corresponding to each rectangle. So let's look at this bottom rectangle and let's find the values of A, B, C, and D. Exactly the same thing we were doing before. So this rectangle down here, look at A. This box A is 1, this box A is 0, so A can be 0 or 1. So we're going to ignore A. B, in this box it's a 1, this box it's a 1, B is always a 1. C, this box and this box is always a 1, and D, this box and this box is always a 1. So this rectangle corresponds to B, C, and D each have to be 1. Okay, and we use the rules that we wrote when we were writing max terms earlier. So to write the sum term corresponding to this, we write down our variable with a bar over it if it's equal to 1, and we OR them together. So this rectangle is the term B bar or C bar or D bar. And this rectangle on top do the same thing. So look at these two squares. A is always a 0, so A is 0. B could be a 0 or 1, so we're not going to use B. C is a 1, and D is a 1. And so for A, since it's a 0, we just write down A by itself. B can be a 0 or 1, we ignore B. C is always a 1, so we write C bar. D is a 1, so we write D bar. And we OR those together. And this corresponds to that upper rectangle. And now we can write our full equation. X is, write the equation, the sum term for the first rectangle. Write the sum term for the second rectangle. And just AND them together. And there's a product of sums. So product of sums representation minimized using a K-map. So it's really exactly the same procedure. All the rules apply. It's just duals. So what is a dual? Copy the zeros to the K-map instead of the ones. Don't copy the ones. Cover all the zeros. Don't cover any ones. Multiple copies of 0 are allowed. Rectangle sides are still the same. Largest rectangles, few rectangles, wrap the edges. And then we're going to write a sum term corresponding to each rectangle, and then we're going to take the product or the AND of those terms to get your final equation. So that's pretty much it. That's all there is to K-maps. Now that's a lot of steps. It's a lot of stuff to keep track of, but it's very algorithmic. It's always the same steps. So the more you do these, the easier they become, the quicker you get at filling in the ones, the quicker you get at writing the equations corresponding to the ones, and so on. So you'll get the hang of it pretty quickly. Just keep practicing, do lots of problems and exercises, ask questions if you get stuck. All right, that's it. Have a good one. Thanks.